Hello everybody and welcome to the final part of our 4-part series on the basics of remote sensing. If you haven't watched the other 3 parts yet, now is the time. They'll all be linked in the video description below, as well as a link to the Geodata Design website where you can request a quote for the software featured in this video, Urtis Imagine. This video will introduce everyone to the wide range of tools available within Urtis Imagine for viewing, analyzing and interpreting spectral characteristics of images. Multispectral images are rendered on a computer display by assigning a single band to red, green and blue color guns respectively. In order to generate the correct color composite image, one must understand the portion of the electromagnetic spectrum that each band is sensitive to. It is important to keep in mind that the band combinations often vary from sensor to sensor. For example, assigning bands 432 from the Sentinel-2A satellite to the red, green, blue color guns will create a natural color composite, while the same composite creates a false near-infrared image in Landsat 7. This is because of the Sentinel satellite bands 1, 3 and 4 are sensitive to blue, green and red light respectively. When images are loaded into the Urtis Imagine viewer, they are displayed using the predefined combinations as defined in the Preferences dialog. By default, all images with 6 or more bands are loaded into the viewer with a 4-3-2 combination. You can also view and change which bands should be used when loading your images through the Select Layer to Add dialog. Next, we will change the preferences to be used for displaying images with 6 or more bands from 432 to 541. When you reload the same Sentinel-2A image, note that it is now displayed using the 541. Once the image is on display, analysts can still change the band combinations by selecting from a list of predefined band combinations from commonly used band combinations under the Multispectral tab. Changing these bands allows us to visually make sense of our data as well as to map and identify different objects from our images. The image will display using the band combinations that you have set. It is important here to understand the fundamentals of the RGB display. The RGB illustration will guide this process. We can use the Inquire cursor to interrogate the pixel values of our image further using the Spectral Profile tool. Use the Spectral Profile dialog to visualize the reflectance spectrum of a single pixel through many bands. This technique is particularly useful for multispectral and hyperspectral data that can have hundreds of layers respectively. This technique allows estimates of the chemical compositions of the materials in the pixel. You can compare the profiles that you generate to those from the laboratory or field spectrophotometers. We will use the Spectral Profile tool to understand the spectral curves of different features identifiable on our images. We select unique features and rename the graphs to assist us in identifying their respective spectral plots. We can also use sensor attributes to plot against actual wavelength instead of a vague band number. This is particularly useful when using a range of sensor models. Spectral characteristics will tend to remain the same for a given spectral range, however, may change drastically between band references. By doing this, we will be able to understand how unique features respond to the different electromagnetic radiation. We can also save the spectral charts for use at a later stage. And with that, we conclude this 4-part series on the basics of remote sensing. If you like what you saw in this video, hit that like button and be sure to subscribe to get notified when we put out more educational videos just like these ones. If you have any comments or questions, be sure to leave them below, and if you haven't yet watched the other 3 parts of this series, be sure to check them out.